Okay, everyone, I'm in an equivalent expressions kind of mood. So we're going to do some hard questions from that category, equivalent expressions, and we'll just walk through some questions together. Something I want to flag as we begin is the primary mode with which I'm viewing these questions. This doesn't apply to every single question, but something I'm noticing on a lot of these questions is that we don't care about all of the details of both sides of the equivalency. So I'll show you what I mean, but it's important to target the right area and not waste time doing all of the math. Okay, so let's jump in. So ax plus 3, that quantity, times the quantity 5x squared minus bx plus 4 is equivalent to 20x cubed minus 9x squared minus 2x plus 12. There's a lot of stuff there, and not all of it is going to matter at the same level. We want to know the value of a, b. Okay, so I always like to start by looking at the answer choices and seeing what I can glean there. And I can at least notice that the 20 and the 40 have something in common. And this 18 and the 24 are both multiples of 6. So there's something going on with that pattern. We don't know yet why that's there, but we'll keep that in mind when we finish the question. Okay, so the first move is to expand this left side. And instead of rewriting it, I'll just go down here and try to do that work. The first bit of expansion is 5ax cubed. And something to know about when you're expanding factors is that, you can kind of look for the first term often, not always, but if it's organized in the normal way, where the highest degree variables are listed first. That's conventional. Notice there's an x here, and then there's just a 3 here. So there's no x. So the highest degree variable is x to the 1. And then in the second factor, 5x squared minus bx plus 4, the highest degree variable is x squared. That comes first. Then x to the 1 comes second, and then nothing at all. Something to notice in those standard situations is that the product of the first two terms is going to give you your largest degree exponent, in this case, x cubed. And I'm confident and familiar enough to say there's no more x cubes coming out of this math. There's nowhere else that's coming from. In other words, I now know that 20 is equivalent to 5a. Right? So without having done any more work, I can tell you 5a is 20. And with just a little bit more work, I can say that a equals 4. And I'm well on my way now. Right? The likelihood that the answer is 18 is now extraordinarily low because a and b are probably integer values. Right? The likelihood that it's not an integer seems very low considering the rest of the math. Okay, so we'll keep going, but that was just the first term. The next term we're going to get is negative ax, or ax times negative bx, which is going to be negative abx squared. Now I'm going to really pay attention to what's happening here. The thing I want is right here, and it's an x squared term. And I already know what a is, okay? So what I'm interested in is not doing the rest of this math. I could say ax times 4, which can be 4ax. I could then do 3 times, all of these different terms. Figuring out what really counts is important here. So I'll show you what I mean. I'll write in blue the stuff I don't really care about, just so you can see it, the rest of the work. Ax times 4, 4ax. Okay, I'm going back to black so you can tell that I really care about this. I've done ax times all 3 of these terms, and I've gotten 3 different terms down here, right? Ax times each of these 3. Now I'm going to do 3 times each of these. 3 times 5x squared is 15x squared. Now, why do I care so much about that? Well, you'll see why in just a second. I'll keep going just so that you don't have to worry about noticing that. I'll now do ax times negative bx. Oh, I'm sorry, I already did that. 3 times negative bx, negative 3bx. I don't really care about that and then 3 times positive 4 for 12. So notice I've gotten 6 terms, 3 from ax times all 3 of these, and then 3 from the number positive 3 times all of these. Okay. Now, why don't I care about these other terms so much? I mean, I could. Another approach would be to focus on, these two right here. But in my case, really all I cared about was AB. Now, I know that all of the x squared terms are negative ABx squared and positive 15x squared, right? So the sum of those two, negative ABx squared plus 15x squared, is equivalent to the x squared term on the right side, which is negative 9x squared. Now, one way of talking about this is I could factor out an x squared. I could say x squared is equal or x squared times negative AB plus 15 is equal to negative 9 times x squared. So you can see our things in parentheses are equivalent. 15, I'll just write this in reverse. 15 minus AB is negative 9. I could subtract 15 from both sides and say negative AB is equal to. After subtracting 15, I get negative 24. And AB, of course, then is positive 24. Okay, so there's our answer. Now, I want you to notice that I actually didn't need this information about A equaling 4. Right? What I really needed to do was find an AB term. I don't know what B is yet. I know I could solve it. Here's another way of doing that. Let's take these blue items and add them together. You could say positive 4ax minus 3bx. Those are all of our x to the 1 terms, right? I'll write a 1 here for clarity and a 1 up here. Those are equal to, negative 2x. Now, having learned that a is 4 from our right at the beginning of our work, I can say 4ax is 16x, right? 4 times 4 minus 3bx equals negative 2x. Subtract 16x. Negative 3bx equals negative 18x. bx is equal to, after dividing by negative 3, 6x. And dividing by x, b is equal to 6. Now you've seen me figure out a and b separately. And of course, then you could multiply to get 24, right? But I didn't actually have to do that. And that's the big lesson of equivalent expressions is oftentimes there's a sort of traditional route and then a more efficient route. So whenever you see these equivalencies, look for efficiencies like I just did. I actually didn't care about A and B separately. I just cared about the product of AB. I could get that directly by paying attention to which terms include AB. In this case, the x squared term was all I cared about, and then combining those like terms. Okay, great. I hope that's helpful. Let's move on to another one. So this question asks, which of the following expressions is or are a factor of 3x squared plus 20x minus 63? Now, there are a couple of different routes here, and I'll highlight them both. The way that I would approach this question normally is to use the answer choices and sort of infer something from them. So if we suppose that the first one works, we would have x minus 9 times something else, some other factor, equals 3x squared plus 20x minus 63. Now, what would that be? Well, you would need, in order to get x times something to equal 3x squared, you would need this first item to be a 3x, right? X times 3x. And then you would also need the negative 9 to multiply times something and equal positive or negative 63. So we need a positive value. So a negative times a positive. And then we're going to need a 7. So the question is, does this math work with the middle term? In other words, I've made it work for my first term, x times 3x, and my last term. And I'm going to confirm that it works by doing the middle calculation, which would be, sort of x times positive 7, so-called. We've done essentially the F and the L in FOIL, and now I'm going to do the O and the I to double check. Okay, so x times 7 is 7x, and then negative 9 times 3x is negative 21x. Oops, I'm sorry, negative 27x. And this looks like, in some ways, kind of close, but off in an important way, right? So we have positive 7x and then negative 27x for a total of negative 20x. So we don't have a factor here, right? Now, at this point, you might be on to the game. You might realize, oh, well, let's just change these signs and see if it works, right? But just in case you're not onto that game, let me start over and say 3x minus 7 and say, okay, what would I expect that other factor to be? Right, so I'll switch my color again. I would need it to be an x here, and I would need to, in order to get 3x squared, right? And let's just see, is this equivalent? That's what we're wondering. It turns out this one's not, just for note taking. The other thing we would need is negative 7 times something is negative 63. So we need a positive 9 here. And then we'll check this work. Again, we've done the F and the L, and now we're checking the O and the I. We did the first and the last. Now we're checking the outside. 3x times positive 9 for positive 27x, and negative 7 times x for negative 7x. And that is equivalent indeed to 20x. Okay, so we got what we wanted. This one works. Roman numeral 2 only. There is another approach, and it's worth paying attention to even if you like that algebraic approach, because there are some questions on which the approach that we just did will work, and there are many, many more questions in which this next strategy is going to be the move, particularly when you don't know what else to do. So let's just see what happens with this. I'm going to be really snarky here. I'm going to pick x as 1. When x is 1, this expression is equivalent to 3 plus 20 minus 63. 23 minus 63 is negative 40. Let's see what's a factor of negative 40. Is this one a factor of negative 40? 1 minus 9 is equal to negative 8. Okay, so it turns out that if I picked 1, both of these are going to work. 1 minus 7, or I'm sorry, 3 minus 7 is equal to negative 4. I'm rushing here a little bit. So that one worked. I would have to try out yet another number to disprove any of them, right? So try out a fairly arbitrary number. You have a calculator on your side, right? So I don't know, you could try out, if you wanted to, 5. 3 times 5 squared plus 20 times 5 minus 63. And we would get here 75, right? 3 times 25 plus 100 minus 63. Okay, so what is that? 175 minus 63. And that is equivalent to 112. Okay, 112. Now see what's a factor. Remember, we said x equals 5. So you go back here. 5 minus 9 is negative 4. So I'm learning something with you here. Because this will work, right? 5 minus 9 is equal to negative 4. And I believe negative 4 is a factor of 112. Right? 112. Yeah. 4 times 25 is 100. 4 times 3 is 12. So 4 times 25 plus 3, or 4 times 28, is equal to 112. Okay, so what we're learning here is that this question guards against the normal strategy. There will be some values for which this is not a factor. We've proven that it's not a factor, right, with the algebraic approach. But it turns out for many numbers, it will be a factor, right? Which is a good challenging question, no doubt. Okay, cool. So that is great to learn the limits of plugging in. If you only know how to plug in, which is a great strategy, I'm telling you, you're going to use it on other questions. This question will surprise us, or maybe it won't surprise us until we get our test results back, right? So we have to be able to factor in order to do this question. Now, I'm certain there are some values that will not work because that's the definition of something being a factor or not. But it appears that, there are many, many values for which this will probably work. We've tried out 2, and we could try out more, but I won't waste our time. Okay. Moving on to the next one. Okay. So this is a question that tests you very simply on your knowledge of exponents and roots. It says the square root of x to the 5 divided by the cube root of x to the 4th equals x to the power of a over b. For all positive values of x, what is the value of a over b? Okay. So all this question wants from you is to be able to recognize that a square root can be written as to the 1/2 power, and a cube root can be written as the 1/3 power. So I could rewrite this as x to the 5 raised to the 1/2 divided by x to the 4 raised to the 1/3. And this is, now we have to know our exponent rules. These multiply. One way I end up describing this to a lot of folks, this is not a mathematically rigorous description, but it can help people, is that exponent rules, you can think about whatever happens at the exponent level as one level down in complexity. So from whatever would happen at the base. So if the base is multiplication, you add the exponents. This would be x to the 8. Just a random example over here. And if we had x to the 5th cubed, you could think, oh, I'm raising this to an exponential power. So what I do with the exponents is one level down in complexity. If you think of addition as the lowest complexity, multiplication is the next level, and exponential operations, that's the third level, right? Raising it to a power as the third level. Well, here we're raising it to a power, so what we're going to do is one level down from that in complexity. This is x to the 15. A more rigorous explanation of this would be to recognize that x to the 5th is just x, 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 and x to the 3rd is x, x, x. And meanwhile, this one would be x to the 5th raised to the cube is x to the 5th times x to the 5th times x to the 5th. And then you could again write this out as 5x's, 5x's, 5x's. Okay, so that's a more rigorous explanation, but simply put, whatever happens at the base level, in this case multiplication, these get added. At this base level, we're raising it to an exponent. That means these get multiplied. That's another level of description. Okay, so going back over here, having known that this is x to the 5/2, and this is x to the 4/3. And then we have to know that similarly to multiplication, where we add, in division we subtract. So this is x to the 5/2. Oh, if we wanted to, yeah, you know what? I think we should. X to the 5/2 minus 4/3. There's, and with algebra, there's always options. There's always other things we could do. In order to subtract these, we need a common denominator, which will be 6, right? 5/2, halves and thirds, we can make into 6s, right? So this would be 5 times 3 over 6 minus 4 times 2 over 6. And this exponential subtraction would be now 15/6 minus 8/6 for a final answer of 7/6. That's a over b, right? So there we have it. Notice once again, I didn't solve for a and b separately. Ultimately, I know them separately now, but I didn't need to solve for them separately, right? Great. I hope those exponential problems seem a little clearer now. Okay, so another question here. 2 over the quantity x minus 2 plus 3 over the quantity x plus 5 is equivalent to rx plus t all over x minus 2, the quantity, times x plus 5, the quantity. Okay. So what is the value of RT? Okay. So if you wanted to, you could pick numbers here. It would be quite tedious, and I don't want to do that. What I'm recognizing right away is that in order to add these two fractions on the left side, we'll need a common denominator, and that common denominator is our denominator on the right side. So we might as well just work with that in mind, right? So the first equation is going to be 2 over x minus 2 times x plus 5 over x plus 5. And then the second equation, not a equals, but a plus. The second equation is going to be 3 over x plus 5. I'll just write it over here for clarity. And then times x minus 2 over x minus 2. That way you can see the same exact denominator. And then you can see that we actually have made it such that we no longer care about the denominator because it's the same on both sides. So knowing your rules of adding fractions, you could say if we have the common denominator, we can just say the numerator of the first plus the second equals the numerator on the right side, right? So we have to distribute here. This is now 2x. This is where everybody's going to mess up. A huge part about doing a great job in the SAT is recognizing where the traps are, even if they seem like easy and silly mistakes. They're mistakes that we want to be highly attuned to. So here we have 2x plus 10, right? 2 times x times plus 2 times 5. And we have 3 times x and 3 times negative 2. And that has to equal rx plus t. So now just combining like terms, the 2 and the 3 are the r, so that's 5x. And then 6, or 10 minus 6 for negative 4. That's rx plus t. And the last thing they're asking for is just the product of r, which is 5, and t, which is negative 4, right? So that's negative 20. By the way, when you've got the right answer, you oftentimes can recognize traps. I see why positive 20 is there. If you forget to include this negative sign as part of what t is, right? Looks like an equal sign now. Let me get rid of that. That negative 4 is positive t. That's an easy way to get the wrong answer with answer choice C. I'm sure the other ones are logical mistakes too, having to do with multiplying by 3, right? Or, some other algebraic error. But when you've got the right answer, you usually can see some other answer that is tempting, even if it's wrong. Great. Moving on.